Now we're going to move on to a more general way of solving uh, linear systems of differential equations. And in order to do this, let's set up a sort of problem that you would want to model with this sort of technique. And so here I have a 10-gallon uh, let's say barrel, and over here, or jug, I have a 5-gallon barrel or jug, some container of water, and they both have water, and both of the waters have some sort of salt water solution or mixture. And then every minute, 2 gallons of water are pumped from the first tank into the second, and the same happens on the way back. 2 gallons per minute are sent back as well. So there's a constant mixture of uh, water going back and forth between the two jugs. And let's say if the first jug had some amount of salt in it and the second jug had some amount of salt in it, could we model how much salt is in either jug at time t? Now, right now I don't have any information on how much is in each jug, but that's okay because we're just for now going to find the general solution for this differential equation. We're going to identify the differential equations or the system thereof. We're going to find a general solution, and then we can go back and put in particulars, like there was 3 pounds in the first jug and 1 pound in the second, or something like that, right? So, but first we want to identify the system itself, and so let's name these things. Let's say the amount of salt in the first jug is x1, and the amount of salt in the second jar is x2. How can I express x1 prime and x2 prime? And so the first thing we want to notice is, the thing about x1 prime is that however much salt it has, right, a full 1/5 of the content of jug 1 has been pumped into jug 2. So that means if there was no water being pumped back, we're just losing 1/5 of its contents at any given moment, which means 1/5 of the salt in addition to other things. So there's a loss then of a 1/5 of the quantity of salt in x1. And that salt goes to the x2, so there's a positive 1/5 of the quantity of the salt in x2. But at the same time, jug 2 is going to take 2 gallons per minute, or 2 gallons, and pump it into x1, and that's 2/5 or 40% of its contents are going to x1. So ignoring, say, this path, it's losing 2/5 of its content per minute at any given moment. And so that means, that jug 1 is gaining 2/5 of x2's content, and conversely, x2 is losing 2/5 of its content. And so that gives us our linear system of differential equations. X1 prime is minus 1/5 x1, 2/5 x2. X2 prime is 1/5 x2 minus 2/5 x1. Now, if I were to write x, what I'm going to call the vector x is just going to be the vector x1, x2. And let's say M, right, is the matrix minus 1/5, 1/5, 2/5, minus 2/5. Then what we're seeing here is we can represent the system of equation as mx is equal to x prime. Right? That exactly this vector, which is, excuse me, that's x prime, that's the derivative of the x vector, and all this over here, that's mx. Right? It is the matrix M acting against the vector x to give you those entries. Right? And so what we want to do now is take advantage of this fact in order to come up with a way of finding potential values for the vector x. Now, let's take just a general look, ignoring the specific values of m and x. Let's just take another look at our differential equation here. And let's just see how nice would it be. Would it be super, super awesome if, let's go with green, let's say vec x were somehow of the form a1, a2, e to the alpha t. Like if it happened to take on that form. Yeah, that would be great. What's so great about that? Then we would get that x prime would be equal to alpha 1, alpha 2, and then when we differentiate this stuff here, the chain rule kicks out a1, a2. It would kick out an alpha, and then we would get e to the alpha t. This is vec x, so we would just get alpha vec x is equal to vec x prime. If that were true, if we assume that this would be the case, then we would get mx is equal to alpha vec x. And what that is telling us then, that would imply alpha is an eigenvalue. Right? What is an eigenvalue of a matrix? It's some constant so that when the matrix acts against the vector, an eigenvector, in this case, then that's equivalent to simply scaling that eigenvector by alpha. And so, if x were expressible as something like this, all we would have to do is try to find an eigenvector that corresponds to alpha eigenvalue. And if we could do so, then all of this work we've done would be consistent and we would have found a solution for this system. Now, is there any reason to think that vec x should actually look something like this? It's a little ad hoc and hand-waving, but when we look at this, these are all linear, right? There's no squares and there's no double prime. They're first order, they're linear. And what we should remember from our discussion of using the characteristic roots method of solving systems of linear equations is that, right, when you have a first order linear homogeneous system, the solutions to that are exponential, right? They're either the regular type of exponential or the complex exponentials, so the sines and cosines, but those are still really exponential. And I know I've asked both of you to verify more than once that solutions to linear homogeneous differential equations are exponential. So the fact is that we once again have first order linear homogeneous differential equations, and so it makes sense that the solutions may also be exponential. And so this is patently a reasonable thing to investigate. So my next step now to see if this idea holds any legs is to take a look at our m here, minus 1/5, 1/5, 2/5, minus 2/5, and see if what its eigenvalues and eigenvectors are, and see if we can turn those into solutions and verify that they are in fact solutions. So, we may or may not remember that the process of finding an eigenvalue or an eigenvector is a potentially frustrating one to do by hand, which is why we are going to utilize our technology here. And oops. And as is often the case, if we've already worked with matrices in other parts of our course, then I have no particular desire to reinvent the wheel. And we should just take advantage of the tools that we have here. So we have a matrix, minus 1/5, 2/5, 1/5, minus 2/5, like we discussed, and I can even show it. We can test it. And there we go. Now, if I want to then go ahead and find its eigenvectors, right? If I want this vec x to be an eigenvector or representable by an eigenvector, it's acting on the right of m. So what I need to be looking for is m dot eigenvectors underscore right. Let me run that. Yes, there we go. And so what we have here are two eigenvalues. The first eigenvalue is 0. The coinciding vector is 1, 1/2, or representative vector of multiplicity 1. The second eigenvalue is minus 3/5. It has representative eigenvector 1, minus 1, also with multiplicity 1. And then we know we're done, not just because this thing said so, but because, as roots to a what would be a quadratic polynomial, because m is 2 by 2, we could only have at most 2 roots, and here they are, right? They're 0 and minus 3/5, presumably. So, taking a look at our matrix here, let's go ahead and test our various solutions. And so I claim that a solution to this differential equation, a possible solution, is vec x is equal to 1 minus 1 e to the 0t, which I suppose is just 1 minus 1. If that's a solution, then we should note that vec x prime is simply going to be 0, 0, right? If both x1 and x2 are constant functions, then their derivatives are 0, and so boom, there it is, right? So let's see, if I took m times vec x, that would be m times 1 negative 1 e to the 0t, and then we should note that that is a product of a matrix, in our case, we should remind ourselves this matrix M with 1, -1, which we just said. Uh-oh, I made a slight boo-boo here. So this would be 1/2. This then should also be 1/2. That's still 0. Because the derivative of 1/2 is still, of course, 0. 1 and 1/2. Well, the point is still that because this is a right eigenvector associated with eigenvalue 0, m times 1 1/2, this term here, that's still going to be equal to 0 times 1/2 e to the 0t, which manifestly still gives us 0, 0. So this, and maybe more easily written, that is a solution to this differential equation. Great. My claim is that another solution is that vec x is going to be equal to, and we look over here, 1 minus 1 e to the minus 3/5 t. Right? And this time we got it right. And so if that's the case, then we should note that, the derivative of x should be, with the chain rule, it should be minus 3/5, 1, -1, e to the minus 3/5 t, which is minus 3/5. This is just vec x, right? This over here is the same thing as this over here. So we just get that whole thing is equal to minus 3/5 vec x when you take the derivative. And so if I were to check this, I would get that m times this vec x is going to be m times 1 minus 1 e to the minus 3/5 t. And again, because 1 minus 1 is a eigenvector, a right eigenvector associated with the eigenvalue minus 3/5, that whole dealio just becomes minus 3/5, 1 minus 1 e to the minus 3/5 t, which is exactly vec x prime, right? And so when we look at both of these, we get that both of these solutions, 1 1/2 and minus 3/5 1 minus 1 e to the minus 3/5 t, both of those are solutions to our system of equations. So if we go back here, what this is telling us is that the general solution is going to be C1, 1 1/2, plus C2, minus 3/5, 1 -1, e to the minus 3/5 t, which is expressible as C1 minus 3/5 e to the minus 3/5 t, and then C1 over 2 plus 3/5 e to the minus 3/5 t. I remember that that's equal to the functions x1 and x2. So that gives me a general system of equations. Wow, those are terrible. I can't wait until my new pen comes in and I can write on this thing like a normal person instead of an awkward angle. So palm doesn't have to touch it. Anyway, so that's the general solution. Let's go ahead and throw in some particular values. Let's say at the start of this thing, there's 3 pounds of salt in the first tank, and let's say there's 0 pounds of salt in the second tank, right? So there's some salt starting here, and it starts mixing to the second tank. There's no salt here, but after the process begins, some salt will be moved from this tank to that tank. It'll move it back in here, but it'll still be pumping salt there. And now we want to know, all right, over time, at any given minute, can I know how many pounds of salt are in each tank? I have no idea if 3 pounds of salt can even dissolve in 10 gallons of water. I'm sure a chemist somewhere knows the answer to that, but not I. Anyway, right, we described our general solution here. So what we're adding to that are the suppositions that x1 at time 0 is 3, and that x2 at time 0 is 0, which means, of course, that, sorry, there should be C2s here, right? C1 minus 3/5 C2 is 3. 1/2 C1 plus 3/5 C2 is 0. And to see where these numbers came from, what I've done here is, I forgot my C2s here, right? This C2 should be down here, which I think would go away. And what I've done is plug in 0 in for t. And when you do that, right, the e to the minus 3/5 t is 1 in each case, and we just get the remaining system of equations. And so just like with the second order differential equations, our whole goal here is to set this up so that we can just solve ourselves a nice little linear system to get C1 and C2, which clearly we have the means to do. And in fact, I'm going to go over to my REF here, copy all of that, blah, 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 da, pop it back in here. No need to reinvent any wheels, doopity doop doop doo. 1 minus 3/5 3 for equation 1. 1 3/5 0 for equation 2. And no third equation, run that. Right, we get that C1 is equal to 3/2, and that C2 is minus 5/2. So going back here, that gives us particular solutions that x1 of t as a function of t is going to be C1, so that's 3/2 minus 3/5 C2, so plus 3/2 e to the minus 3/5 t. x2 of t is going to be 3/4, right? 1/2 C1 plus, sorry, negatives cancel, minus 3/2 e to the minus 3/5 t. And great, I didn't actually capture any of that because I had the wrong screen on. Hopefully if we're doing this stuff live for some of my classes, then you'll be able to tell me it in real time when I'm doing things like that. But, right. So let's check. At time 0, e to the minus 3/5 t is just 1. So we start with 3/2 plus 3/2 equals 0. And at time 2, hold on a second here. Oh my god. Alright, so there's an error here, isn't there? This isn't a 1, this is a 1/2, right? To be consistent with this 1/2, if I run that, my solution is actually 2 and minus 5/3. So let me write those instead. Right? And if it's 2 and minus 5/3, then this should simply read 2 and minus 5/3 times minus 3/5 is just 1. On the other hand, 2 times 1/2 will give me 1. And minus 5/3 times 3/5 will give me -1. Yeah, there we go. Let's just leave it at that. Alright, that makes a lot more sense. I was starting to think something really strange had happened. So at time 0, what we get is 2 plus 1, 3 pounds, right, in tank 1. At time 0, 1 minus 1, or 0 pounds, right, in tank 2. And then as time goes to infinity, the e to the minus 3/5 t value tends to 0. So we're looking at stabilizing towards 2 pounds in tank 1 and 1 pound in tank 2. And if we think about it, if you had 2 pounds in tank 1 and 1 pound in tank 2, let's say you started there, then in our initial setup, that means 1/5 of our 2 pounds, or 2/5 of a pound, is moving from tank 1 to tank 2. And then 2/5 of 1 pound, or 2/5 of a pound, is moving from tank 2 to tank 1. So at that point, you actually balance it out equivalently. Both of these, if you put in those values, 2 and 1, 2 and 1, your x1 prime and x2 prime are both 0. So you just have no change whatsoever, and everything is perfectly balanced. And that is the eigenvector, or a multiple of the eigenvector associated with x prime being 0, right? If you have twice as much in the first tank as the second tank, everything balances out. And what we have as a more general phenomenon is that given some other setup, whatever the initial values are, we start with 3 and 0, say, but as time tends to infinity, it starts to balance to the 2 and 1. That is the stable solution. So, Uh, the basic idea then is that if M has eigenvalues, value vectors, lambda 1, comma, v1, lambda 2, v2, then a general solution for x can be, I'm just going to write it as a big summation, the sum of c1 or ci, vi, e to the lambda I t. That this is going to be the form of your general solution. Now, some things we ignore by saying that out loud. It's the same things we kind of ignored in the first case, in the second order differential equation. So some things we're ignoring are multiplicity. Right. Another thing we're ignoring is complex roots. And the third thing we're ignoring is non-homogeneous. But that's okay, because in the second order and higher order cases, we figured out how to deal with multiplicity by basically throwing x in front of stuff. We figured out how to deal with complex roots by turning them into sine and cosine expressions. And, we sort of figured out how to deal with non-homogeneous by finding any solution to the non-homogeneous case and then throwing the general homogeneous solution on top of that. So it's basically the same strategies we're going to use here, right? The standard solution to a higher order homogeneous differential equation without any of this stuff was just a bunch of e to stuff x's or e to stuff t's like we have here. And so we're going to generalize the types of solutions that work there to ones that work here. And hopefully that makes sense. Thank you very much.